Hello, welcome to Alpha Beta Tutorials. In this video, we will explore heat capacity, specific heat capacity, and the principle of method of mixtures. Stick around as we break down these concepts in a clear and straightforward manner. Let's roll. First of all, what is heat? Heat is a form of energy associated with the motion of atoms and molecules in a substance. So the movement of the atoms and the molecules in a substance determines the heat energy of the substance. The faster the atoms and molecules move, the higher the heat energy, and vice versa. The unit of heat is joule. That's the SI unit of heat. Now let's assume we have water in this glass and we are heating it from below, and the initial temperature θ1 of the water is 30 degrees Celsius. Then the heat energy required to change the temperature of the water by 1 degree Celsius, that is to move it to 31 degrees Celsius, which is a change in temperature of 1 degree Celsius. The heat energy required to change the temperature of the water by 1 degree Celsius or 1 Kelvin is the heat capacity of the water. Heat capacity is denoted by the letter C, and heat capacity is the amount of heat energy required to raise the temperature of a substance by 1 Kelvin or 1 degree Celsius. Mathematically, heat capacity is equal to the quantity of heat divided by temperature change. So heat capacity is denoted by C, and let's represent the quantity of heat with Q, and temperature change is delta theta. So the SI unit of heat capacity is, we have heat at the top, which is measured in joules, and temperature change is either in Kelvin or degrees Celsius. So we have joules per Kelvin since the temperature is at the denominator, or joules per degree Celsius since temperature can be measured in either Kelvin or degrees Celsius. And also we can cross multiply. So the quantity of heat is equal to the heat capacity times the change in temperature. Now let's solve this example. Heat is supplied to a body of heat capacity 400 joules per Kelvin. So the heat capacity is 400 joules per Kelvin. The temperature of the body rises from 20 degrees Celsius, that is the initial temperature θ1, to 90 degrees Celsius, that is the final temperature. Calculate the quantity of heat supplied. And here the quantity of heat is given by the heat capacity times the temperature change. And the heat capacity here is 400 and the temperature change is 90 minus 20. That is the difference in temperature. And 90 minus 20 is 70. So we have 400 times 70 giving us 28,000. So the quantity of heat supplied is 28,000 joules. Again, let's assume we have water in this glass and the mass of the water is 1 kilogram. And the initial temperature is 30 degrees Celsius. And we want to heat the water so that there will be a temperature change of 1 degree Celsius. That is, we want to heat it to a final temperature of 31 degrees Celsius. Then the heat energy required to change this 1 kilogram mass of water by 1 degree Celsius is the specific heat capacity of the water. Is denoted by the letter C. So specific heat capacity is the amount of heat energy required to raise the temperature of a unit mass. That is, the mass should be 1, either kilogram or grams, of a substance by 1 degree Celsius or 1 Kelvin. So the only thing that changes here is the unit mass. For heat capacity, the unit mass doesn't matter, but for specific heat capacity, there should be a unit mass of a substance. Mathematically, specific heat capacity is equal to the quantity of heat over the mass times the temperature change. Specific heat capacity is denoted by C. Let's represent the quantity of heat with Q, and mass is M, and delta theta represents the temperature change. So now the quantity of heat here is measured in joules, and we have mass at the denominator, so per kilogram, and temperature is also per Kelvin or per degree Celsius. So the unit is joule per kilogram per Kelvin or joule per kilogram per degree Celsius. And also we can cross multiply, and the quantity of heat will be equal to mass times specific heat capacity times temperature change. And now the relationship between heat capacity and specific heat capacity. Now specific heat capacity is the quantity of heat over mass times temperature change. And this can be written as 1 over mass times quantity of heat over temperature change. Because when we multiply the numerator, 1 times quantity of heat is quantity of heat, and mass times temperature change is what we have here. But quantity of heat over temperature change is equal to heat capacity. So let's replace it. And now the LCM is mass. So let's multiply through by mass. We have mass times specific heat capacity is equal to mass times 1 over mass times heat capacity. And we can cancel out mass here and have mass times specific heat capacity is equal to heat capacity, or heat capacity is equal to mass times specific heat capacity. And this is the relationship between heat capacity and specific heat capacity. Different substances have different specific heat capacities, and they play a crucial role in understanding and predicting how substances respond to changes in temperature. For example, substances with higher specific heat capacities require more heat energy to change their temperature. Water, for instance, has a relatively high specific heat capacity, making it effective at moderating temperatures in the environment and contributing to the regulation of Earth's climate. Now let's solve some examples. Example 2. How much heat is required to raise the temperature of 3 kilograms of water by 30 degrees Celsius? The specific heat capacity of water is 4,200 joules per kilograms per Kelvin. The quantity of heat is given by the mass times the specific heat capacity times temperature change. and the mass here is 3 kilograms. Specific heat capacity of water is 4,200 joules per kilograms per Kelvin, and the temperature change is 30 degrees Celsius. So when we multiply, we have 378,000 joules. Example 3. A quantity of water of mass 265 grams, originally at 23 degrees Celsius, is supplied with 25 kilojoules of heat. Given that the specific heat capacity of water is 4,200 joules per kilograms per Kelvin, determine the final temperature of the water. The quantity of heat is given by mass times specific heat capacity times the change in temperature. But the quantity of heat here is 25 kilojoules. Kilo means 1,000, so the quantity of heat will be 25,000 joules. So we replace Q with 25,000 joules. The mass is 265 grams, but looking at the units, we have kilograms here. So we have to change the mass to kilograms before we use it in the formula. So the mass is 265 grams. We divide by 1,000 to change it to kilograms. And the specific heat capacity is 4,200 joules per kilograms per Kelvin. And now the temperature change. The initial temperature is 23 degrees Celsius, but we don't know the final temperature. So the change in temperature is going to be final temperature, temperature 2 minus initial temperature, 23 degrees Celsius. So here we have 25000 is equal to, this would give us 0.265 times 4200 times change in temperature. And now 0.265 times 4200 will give us 1113. And we have theta 2 minus 23. And let's divide through by 1113. So we have 25,000 divided by 1113 is equal to final temperature minus initial temperature. And 25,000 divided by 1113 is 22.46 to 2 decimal places. And now let's bring the 23 to this side to add. So 22.46 plus 23 is equal to the final temperature. And 22.46 plus 23 is 45.46. So the final temperature, theta 2, is 45.46 degrees Celsius. Example number 4. A piece of iron of mass m is heated from 27 degrees Celsius to 37 degrees Celsius. If it absorbs 3000 joules of energy in the process. Calculate the value of M, and the specific heat capacity of iron is given to be 462 joules per kilograms per Kelvin. Now the quantity of heat is equal to mass times specific heat capacity times change in temperature, and the heat is 3000 joules. So we replace it. 3000 is equal to mass is M, is unknown. Specific heat capacity of iron is 462 joules per kilograms per Kelvin. And now the temperature change. The final temperature is 37 degrees Celsius minus 27 degrees Celsius. So we have 3000 is equal to mass times 462 times, now 37 minus 27 is equal to 10. And 462 times 10 is 4620. So we have 4620 M. So now we divide through by 4620. So the mass is 3000 divided by 4620, which is 0.65 kilograms to 2 decimal places. Example 5. Explain the statement. The specific heat capacity of water is 4200 joules per kilograms per Kelvin. So the specific heat capacity of water is given, and we are going to use the definition of specific heat capacity to explain the statement. So this statement means that the amount of heat energy in joules required to raise the temperature of 1 kilogram of water by 1 degree Celsius or 1 Kelvin is 4200 joules per kilograms per Kelvin. Our next subtopic is falling body. Consider a body of mass m held at a height h above the ground. The potential energy of the body is given by the mass of the body times the acceleration due to gravity, g, times the height of the body above the ground. As the body falls, the height of the body decreases, and so the potential energy of the body also decreases, since the height h is directly proportional to the potential energy of the body. And at the instance the body hits the ground and stops, the height h reduces to 0, and so all the potential energy is lost. But according to the law of conservation of energy, energy can neither be created nor destroyed, but can be transferred from one type to another. Hence, the lost potential energy is converted to heat energy, light energy, sound energy, and so on. This explains why at any waterfall site, the water at the base is warmer than the water at the top. Now, assuming all the potential energy is converted to only heat energy, then we have potential energy is equal to heat energy. Potential energy is mass times acceleration due to gravity times height, and heat energy is equal to mass times specific heat capacity times change in temperature. Here we can cancel the mass. So we have acceleration due to gravity times height is equal to specific heat capacity times temperature change. And so we can use this to solve some examples. Example 6. A quantity of water falls through a height of 50 meters. Determine the temperature rise at the bottom of the fall. Neglect heat losses. Specific heat capacity of water is 4,200 joules per kilograms per Kelvin. Acceleration due to gravity G is equal to 10 meters per second square. We are neglecting heat losses. So it means that all the potential energy is equal to heat energy. So potential energy mgh is equal to heat energy mass times specific heat capacity times change in temperature. Now we cancel out the mass and we have Gh is equal to C times change in temperature. Acceleration due to gravity is 10. The height is 50 meters. And the specific heat capacity of water is 4,200 joules per kilograms per Kelvin. And we want the temperature change, delta theta. That is the final temperature minus the initial temperature. So 10 times 50 is 500. And we divide through by 4,200 to get the temperature change. So the temperature change is equal to 0.119 degrees Celsius. When hot water and cold water are mixed together, provided there is no loss of heat energy, what happens is that the hot water will lose heat and the heat lost will be gained by the cold water until they all attain a final steady temperature. When they attain the same temperature, then thermal equilibrium is said to have been reached. And this brings us to the principle of method of mixtures. The principle of method of mixtures states that when two substances at different temperatures are mixed together, the heat lost by the hotter substance is equal to the heat gained by the colder substance until they attain the same temperature, provided there is no loss of heat energy. This principle is based on the law of conservation of energy. Now let's solve some examples using this principle. Example 7. Water of mass 3 kilograms at a temperature of 80 degrees Celsius is added to 5 kilograms of water at 5 degrees Celsius. Calculate the final temperature of the mixture. Let the final temperature be T. And according to the principle of method of mixtures, heat lost by hot water is equal to heat gained by cold water. For the heat lost by hot water, we have the mass of hot water, specific heat capacity of water is a constant. So whether hot or cold water, the value is still the same. So mass of hot water, specific heat capacity of water, then the temperature change of the hot water. And for heat gained by cold water, we have mass of cold water, specific heat capacity of water, and then change in temperature of cold water. Specific heat capacity of water is a constant, so we can cancel it out. So we have mass of hot water, temperature change of hot water is equal to mass of cold water, temperature change of cold water. Now, what is the mass of hot water? The temperature will tell which water is cold and which water is hot. 80 degrees Celsius is hotter than 5 degrees Celsius. So the mass of the hot water is 3 kilograms. So we have 3 here times temperature change. 80 degrees Celsius is hotter than 5. So this is the hot water and it's going to lose heat to the final steady temperature. So that will be the temperature change. 80 minus final temperature. So it will lose heat from 80 and cool all the way to the final steady temperature. And for the cold water, the mass is 5 kilograms. And let's look at the temperature change of the cold water. So heat lost by the hot water. The hot water has lost heat by cooling from 80 degrees Celsius all the way to the final temperature. And the cold water is going to gain that heat by warming from 5 degrees Celsius to the final temperature. So it's going to increase in temperature from 5 degrees Celsius to this final temperature. So this final temperature is bigger than 5 degrees Celsius. So we do the subtraction this way. Final temperature minus 5. We subtract the small temperature from the big one. We expand. 3 times 80 is 240. 3 times T is 3T. 5 times T, 5T. 5 times 5, 25. We group like terms. Let's bring the 25 to the left hand side to add. We have 5T here. Let's send 3T to the right hand side to add. And 240 plus 25 is 265. 5T plus 3T is 8T. And we divide through by 8 to get the final temperature. So T is equal to 265 divided by 8. And 265 divided by 8 will give us 33.125 degrees Celsius. This is the final temperature of the mixture. Example 8. A quantity of water of mass 120 grams and temperature of 90 degrees Celsius is mixed with 180 grams of water to obtain a resultant mixture of temperature 52 degrees Celsius. Calculate the temperature of the cold water. Let the temperature of cold water be X. The heat lost by hot water will be gained by the cold water. Now, the heat lost by hot water is going to be the mass of the hot water, specific heat capacity of water. As for specific heat capacity, whether hot water or cold water is a constant. And then the temperature change of the hot water. Now heat gained by cold water is going to be mass of the cold water, specific heat capacity of water, and the change in temperature of the cold water. So specific heat capacity of water can cancel out and we have mass of hot water temperature change of hot water is equal to mass of cold water temperature change of the cold water. So now what is the mass of the hot water? Now a quantity of water of mass 120 grams and temperature of 90 degrees Celsius is mixed with 180 grams of cold water. So the hot water is the 90 degrees Celsius and it has a mass of 120 grams. But we have to change it to kilograms. That will be 120 over 1000. What will be the temperature change of the hot water? This is the temperature of the hot water, 90 degrees Celsius, and it cooled to a resultant mixture of temperature 52 degrees Celsius. So it moved from 90 to 52. So that will be the temperature change. The mass of the cold water is 180 grams. To kilograms, we divide by 1000. What will be the temperature change? We said let the temperature of the cold water be X. And the cold water is going to gain the heat and increase its temperature to 52 degrees Celsius. So the change in temperature is going to be 52 minus X. 120 divided by 1000 is 0.12, and 90 minus 52 is 38. 180 divided by 1000 is 0.18, and we have 52 minus X. Now 0.12 times 38 is 4.56. So we expand. 0.18 times 52 is 9.36 minus 0.18x. We group like terms. So let's bring 0.18x to this side and bring 4.56 to subtract from 9.36. So we have 0.18x is equal to 9.36 minus 4.56 is 4.8. Then we divide through by 0.18. So 0.18x over 0.18 is equal to 4.8 over 0.18. We cancel out and we have x is equal to 26.67 degrees Celsius. And that is the temperature of the cold water.